The second question is, I'll give you a chance to read it. Okay, maybe that'll take too long. The second question's getting at, it's a mathematical question. They want an equation. Object hollow sphere experiences no gravitational force from the mass of that sphere. Means if you're standing inside a hollow sphere, imagine yourself there. In fact, let's draw that. Here's a hollow sphere, here's you standing inside, and you're experiencing no gravitation. The theory here is that, same as the question earlier, you're in equal position from all masses, so therefore you're pulled equally in all directions, creating a kind of a null space with no gravitation in the middle. Now that's just to imagine that. Now the second part of that's just building the question. The second part here is what it's really all about. Use this result and Newton's law of gravitation, which is that Fg equals big G big M little m over r squared, to show that G increases linearly as you move from the centre of the Earth outwards to the surface. So it's not explicitly mathematical, but you notice you've got volume of a sphere here, you've got density as mass over volume, and you've been told about Newton's law of gravitation. So it's highly likely it's going to be a mathematical question, and it's much easier, I think, to answer that way. So what are you being asked? You're being asked to show that G increases linearly. That means G is proportional to, as linearly as one moves from the centre of the Earth. That means G is proportional to the radius, or the distance from the centre of the Earth. So that is what you're after, an equation which shows that. And putting it in another form, you want to show that G is equal to some constant times by this radius. Okay, going from the general relationship to a specific mathematical relationship. So how do we do that? We have to link all of these formulas that they've told us about. There's 3 of them. There's actually 4 of them, because you've also got Fg equals mg, and that'll help us a little bit later on. Now we have to remember there's one tricky part, and that's that this mass here, when you're talking about the density of the Earth, is a capital M. That's a big M in this equation. So let's just proceed and stick all of these things together and see what we come up with. Go to a different colour so it's a little bit easier to follow. We've got Fg is equal to mg, which equals big G. Look at all these big M's, little m's, big G's, little g's. Okay, so I think we can use this. And we've also got the density, which is the symbol rho. Greek letter RHO is how it's spelled, but it's said rho, like row your boat, but without the emphasis on the W, like row, not row. Anyway, rho is big mass, big M, over the volume. Alright, so there was one other equation, that was the volume. Okay, same V again. Volume of a sphere is 4/3 pi r cubed. Okay, so we can actually link these bottom 2 equations together with V to eliminate one of them altogether. That'll be a little bit nice. In fact, my brain's jumping ahead and it's thinking we're going to see this M, the subject, and we'll substitute it for this M. But there is one minor cancellation we can do. That M and that M can cancel. So we get rid of, I don't know if that's totally, yes it is, because we're trying to get G by itself. That's good, so we're going to get G out the front by itself. We're going to substitute V in here for this V, and we're going to rearrange to make M the subject. And then we're going to put that M in there and calculate it all through. So let's just follow through with that. We've got, I'm rearranging this formula to make M the subject so it's a little bit easier. M equals rho times the volume, which equals rho times 4/3 pi r third. Okay, so that was a nice, quick and easy way of doing that. So now we're going to put this, which equals M, we're going to put that into this position up here. So that'll give us G equals big G, which is the universal gravitation constant, and times by rho 4 third pi r third, and it's over r squared. Okay, you can go back and check all of that, watch the video again if you like. Now something really cool here, the r squared is going to cancel out the cube part, and that leaves just the r by itself, which is what we want. We want g equals some constant times r. I won't finish that there, you can see exactly how it's going to go, and that shows that the the gravitational field strength is linearly proportional to, or directly proportional to, the radius, the further out you go from there. And that corresponds in the very first question, which you can jump back and have a look at that video, to the linear portion of the graph. Remember, it went up and then it dropped off exponentially according to the inverse square law. But in that initial part, that initial section, it was a linear trend, which is in keeping with our equation that we've just found there.